Hello class, this is section 3.2, and in this video I just want to explain something that I don't think the book covers very well. So this is the case where our characteristic equation has a double root r, so it only has one root, one real root, and we want to show why we have the solution ERX and the solution XERX. So the first solution just comes from making the substitution, and that should be very familiar to you. If you don't understand why we have this first solution, ERX, please let me know. The second solution is a bit mysterious, and I just want to explain where this comes from. So this really comes from looking what happens when we have a double root. What happens when a polynomial is a double root? Let's call this polynomial PR. When this polynomial has a double root, we have like PR equals 0. This implies that the derivative of the polynomial also has a root r. So this is the fact where this comes from. There are two ways to look at it. There's one way to look at it geometrically, and there's another way to look at it algebraically. Let me explain the geometric explanation first. So what happens in a quadratic equation when you have a double root? You would have a parabola, and the double root is precisely where you have a little curve over here, where there's a little double when you have a tangency to the line. So either looks like this or looks like this. So this is where the double root is, either here or here. What is the slope of the line at R? So slope is 0. So that means the derivative of R is 0. That is one way to look at it, using the geometry. There's also another way to think about things, and that's using the algebra. For this way, consider that PR equals, when PR has a double root, what this means algebraically is that you can write PR equals R minus R squared. So that's what it means to have a double root. It means that you have a root and it's also squared. If we take the derivative of this function using the chain rule, we get this. But clearly, this implies that the derivative also has a root at R. Right, so that's the first thing that's the initial principle to keep in mind. If a quadratic polynomial has a double root, it means that its derivative also has that root. So let's see how we can use that fact here. Right, so first we want to write down, so let y2 be our function, XERX. Let's consider the derivative. We have to use the chain rule here, so we have ERX plus XRERX using the product rule. And then we use the product rule again to find the second derivative. Here we get RERX plus RERX plus XR squared ERX. So notice how the product rule here forces there to be two terms of this ERX thing. Right, so plugging this in, the original equation, y double prime plus ay prime plus by equals 0, we can simply get 2r ERX plus XR squared ERX, that's our y double prime, plus a times our y prime plus b times our y. So now we have to gather terms, and here's what we do. ERX terms, we have r squared plus AR plus B times X ERX plus 2R plus A ERX. So first of all, we know that R is the root of the polynomial P, and the polynomial P is exactly this polynomial. So we know that this is in fact 0. So this entire term is 0. So we just have to look at the second one. However, 2r plus a is equal to p prime of r. Since r squared, you take the derivative of r squared, you get a 2. Take the derivative of ar and just get a. And this is also equal to 0. And we have 0. And therefore, indeed, y equals xe rx is a solution to the differential equation. So observe this little symmetry here. Algebraically, PR equals r squared plus AR plus B. Taking the derivative of this PR, we have a 2 that comes down here. Similarly, using the product rule, we have two terms, a 2r term for the ERX component here. So the fact that XERX is a solution is connected to the fact that both the function P, the polynomial P, and the derivative P prime have a root at R. And that is why we have this set of solutions when we have a double root. A similar explanation occurs for higher order equations. I'm not going to make a video for that, but similar principles hold. For instance, if you have a triple root, then you know that y, the polynomial p, the derivative p prime, and the second derivative p double prime have the same root r.